Alright, welcome back everyone to functional analysis. So currently we are in the middle of the proof of the equivalent norm theorem. So it's displayed here on the page. The last video we completed the proof of two of the three statements in the theorem. So just to recall what it is about, given a nonlinear space, a non-normed linear space. First statement, it is finite dimensional if and only if every closed and bounded subset is compact. That's the part which is still outstanding. We did the other two parts, namely if that space is finite dimensional, then it is always complete. And any two norms on the space are equivalent in the sense as written here, meaning there exists these constants C and D, and you have the double inequality between the two norms. Okay, so this theorem, in a nutshell, it of course explains why finite dimensional spaces are, well, one could say boring, because, well, they're always complete, and as far as topological properties are concerned, as soon as you have control over one norm in that space, you have control over all the other norms because all the norms are equivalent. So that makes these spaces, well, somewhat less interesting, and actually for this reason, because of this theorem, we're not going to be concerned much with finite dimensional spaces at all in this class. Okay, so almost everything is going to be infinite dimensional where this theorem does not apply. Okay, so we proved, as I said, the completeness part. We had some preparation, we had some estimates by triangle inequality Cauchy-Schwarz. We defined a map between the finite dimensional vector space and the coordinate space f to the n. That map is linear, bounded, and bijective. And then using the inverse, you prove the completeness and you prove the equivalence of the norms. So now what is outstanding is the part up here, namely finite dimensional if and only if every closed and bounded subset in the space is compact. So I started this last time. I immediately jumped to sort of the interesting direction, right? It's an if and only if statement, so there's two directions have to be shown. I said if the space is finite dimensional, then it's clear and that every bounded and closed set is compact. I didn't write anything down. The writings here on this page are already concerned with the other direction, so maybe because we're still early on in the class, before we get to the other direction, let me indeed then write down some details for the first direction. So if x finite dimensional, x is finite dimensional, then what I have to do is I have to take an arbitrary closed and bounded set and I have to show it's compact, right? So if x is finite dimensional, let k in x be closed and bounded. Then I claim you can immediately conclude that k has to be compact. And why is this? Well, you use the map in the first part of the proof that gets you from that space x into the coordinate space Fn. Because in the coordinate space Fn you have the Heine-Borel theorem. And Heine-Borel theorem tells you sets are compact if and only if bounded and closed, right? So let's write this down. We have the identity that k is equal to, well, look at t minus 1k. So this is just the image of my set k under the inverse of the map that we discussed earlier. So this is an element or is the set, I should say. It's a set in Fn. And I claim this set has to be bounded and closed. And why is this? Well, for one, we had the boundedness. Remember, we had an inequality in the first part of the proof, which was t minus 1x in the Euclidean norm is less than or equal a constant norm of x, right? So if you start with an element here in k, and k is bounded after all, then this inequality tells you immediately that the image of the set K under the inverse of T is also bounded, right? Because here the right-hand side is bounded, okay? So boundedness you get for free, and closedness you get even easier, because how do you show that something is closed? Well, you take a sequence with terms in the set which is convergent, and then you have to show that the limit is also in the set. So you do this, you take a sequence here in T minus 1K by the bijectivity of the map, convergent sequence that is, by the bijectivity of the map that immediately corresponds to a convergent sequence in K, but K is closed, so that convergent sequence has to have limit inside K, and then you apply again the inverse map T minus 1, and you conclude that the original sequence, its limit is in T minus 1K. Okay, that's an easy exercise. So now what you have, after you have established boundedness and closedness of T minus 1K, well, since this is a subset of Fn of a coordinate space, and F is either the real number field or the complex number field, you have a bounded and closed set in, well, Rn or Cn, and then you use Heine-Borel theorem, right? So this is actually compact here, is compact, okay? And now how do you get to K? So far it's not an equality yet. Well, now you apply T to it, right? So now what happens is you take a compact set, this guy here, and you stick it into the map T. Yeah, but the map T was linear and bounded. And the first theorem that I proved in this class is those linear bounded maps on any normed linear spaces, they are continuous, right? So what you have here is you take compact set and you stick it inside a continuous map. Well, then there's a theorem from the metric space module that you will end up with something compact. And you know precisely what you end up with, which is K, right? So that's how you show that K has to be compact, okay? Good. All right, so now let's do the reverse direction. Let me erase this and move this text now further down. So that is harder, the reverse direction. So conversely, if every bounded closed set is compact, now I have to show that the space X is finite dimensional. Okay, so first some preparation for this. So if a set is compact, in metric space modules, you have learned at least 3 types of compactness. There's the original definition of compactness, saying that, well, set is compact if every open cover has a finite subcover. Then there is a notion called sequential compactness. This has to do with sequences having convergent subsequences, and the limit of those convergent subsequences is in the set. And then there's the third part, which some people call pre-compactness, others, like myself, call it totally boundedness, okay? Now, these 3 notions, they are in general not equivalent, but what is true, if a set is compact, then it is automatically totally bounded. And totally bounded means you can cover the set by finitely many balls of arbitrary small radius, okay? If you're a bit rusty about this concept, have a look in section 1.1 of the lecture notes there, it's all reviewed, okay? So now, by assumption, a compact set such as the closed unit ball, because it is bounded and closed, so it's compact by assumption, it is also totally bounded here. I will pull the argument here through with the unit ball, although as you quickly realize the radius doesn't play any role whatsoever. I could have done this with any radius. Okay, but let's do it with the unit ball. So totally boundedness means, this means I can cover it with finitely many balls of arbitrary small radius. So, but this means we can find finitely many x1 up to xn in the closed ball, such that well, the original one is covered by the union j1 to n. Now, of balls of arbitrary small radius, here I will do the radius 1 over 2. It doesn't matter, you know, you could have chosen any other finite number. Okay, now set U as the span, which is the set of all linear combinations of those centers x1 up to xn. Okay, so this is for sure, U is for sure, it's a subspace, and it's for sure a finite dimensional vector space. It has dimension at most n, right? So notice, by the way, those xj's, they don't have to be linearly independent, so the dimension is not guaranteed to be exactly equal to n, but U for sure is finite dimensional, okay, at most dimension n. Okay. As such, we have shown in the first part of the proof, it is a complete space, and it is also a closed space, right? So let's write this all down, which is finite dimensional, complete. That's what we showed in the first part of the proof. Now the closedness we didn't show in the first part of the proof, because this is obvious. If you have a sequence of elements in U, then each term in the sequence is a finite linear combination of those xj's. So any limit, if that sequence were convergent, would also be a finite linear combination of those xj's. So again, it would be in U. So this is closed, okay? Now what we do is we pick an arbitrary and pick an arbitrary x in the closed unit ball. So now what I will show is that actually the closed unit ball B10 with a bar on top is contained in U, and that's why it has to be finite dimensional. And since this argument will work for any ball of any radius, it means that the whole space can have at most dimension n. Okay, so how to show that the ball is contained in U? Well, pick an arbitrary element x and show that it's, well, inside U. Okay, so by this one here, we will construct a sequence by star. We can find element U1 in U and x1 star in the closed unit ball, so that, well, x is equal to U1 plus x1 star over 2. Okay, so why is this true? Well, this is precisely what the yellow star says there on top. So if I start with something in the left hand side, then it is at most distance 1/2 away from the closest center, so to speak, right? So that's why that element x1 star, which has length, which has norm at most 1, right? So that is certainly true. Yeah, but now what you do is you iterate this argument. So now you started with x and you have found U1 and x1 star. So now what you do is you start with x1 star and find U2 and x2 star, so on and so forth. Okay, iterating this argument, we next can find U2 in U and x2 star in B10, so that x1 star is U2 plus x2 star over 2, for the same reasoning as we had it in the first iteration of the process, right? Yeah, but that together now, let's write it on the next page on top. What have I just achieved? So I have x was U1 plus U1 star over 2, but now not U1 star, it was x1 star. x1 star, but now x1 star was U2 plus x2 star over 2. So you substitute this in, do the little algebra here, and out comes x2 star over 4. Yeah, but since U is a subspace, linear combinations of elements in U again are in U. Okay, so this is in U. Okay, so now you continue this argument, continuing in this fashion. For arbitrary x in B10 closed and any natural number n, we can find u sub n in U and xn star in the closed ball, so that x is equal to un plus xn star over 2 to the n, right? So compared to this equation up there, you would use a relabeling. You would relabel this element here as sort of your u2, and then the x2 star over 4 would correspond precisely to this in the second iteration. Okay, so what have you achieved then? But then, well, then x minus un is less than or equal to the norm of xn star to the 2n. Well, the norm property lets me pull out the factor 1 over 2n, it's positive, and then the length of xn star, because they are sitting inside the unit ball, is at most 1. So this is less than or equal to 1, and obviously this quantity here, as n goes to infinity, goes to 0. Okay, so the sequence un, which is in U, converges to x. Yeah, but now x also has to be in U. Why is this? Because U is closed. The subspace U is closed. It's a finite dimensional subspace, they're always closed. Okay, I gave the argument earlier why that is the case. Okay, so that means we started with an arbitrary x in the closed unit ball. Now we have shown it is in U, hence B1 star closed is sitting inside U, as I promised it earlier on. And in all this argument here, the radius of 1 never really played a role. If you have here an arbitrary radius, say r, here if you have, instead of 1, you have r, you would then have an r up here, right? But since r is fixed, as n goes to infinity, this would still all go to 0, okay? So this means any ball of any finite radius is contained in the finite dimensional space. Yeah, but this means that the space itself must be finite dimensional, okay? In turn, x must be contained in U. Well, let's write the containment like this, but U is finite dimensional, so the dimension of any subspace cannot exceed that dimension of U, which is at most n, right? So you have it. So x indeed has to be finite dimensional. Okay, very good. So this closes the proof of the finite norm theorem, equivalent norm theorem. 3 assertions. Finite dimensional if and only if every closed and bounded set is compact, completeness, and the equivalent norm property. Okay, good. So now let's discuss finally some examples of normed linear spaces that we will encounter frequently in this module. The first one is a function space. These are continuous functions, real or complex value, doesn't matter, defined on the closed unit, on the closed interval from 0 to 1 on the real line. Okay, so denote the vector space of continuous functions, real or complex valued, on 0, 1, real. Okay, this will be our notation with values in F. Okay, so now it turns out you can define infinitely many norms on that vector space X to turn it into a normed linear space, but for our purposes the following ones will play an important role. Okay, so we can turn X into a NLS by either considering the following norm. So it gets this symbol F, and then there's an infinity here as a subscript. This is notational convention. it will be, you look at f of x, you stick it into the complex modulus, and then you optimize it over the closed interval 0, 1. Well, here a theorem from real analysis says that this supremum is actually attained for a continuous function at a point inside 0, 1, because 0, 1 is compact, right? So this supremum is actually in maximum, okay? That's the first one we can look at. And then the other ones, that is a family of norms, or by introducing these so-called p norms. So here p would be from 1, well, strictly smaller than infinity. So let's write it out. Integral 0 to 1 f of x p d of x, and then the pth root, and that is for p from at least 1 to any finite value. Okay, there's a reason why we don't want to go to 0. I mean, these quantities as they're written here, they still make sense if p is in between 0 and 1, but then it's no longer going to be a norm. Okay, so this, I mean, we still have to check that these are actually norms. So right now it's just a definition. Here, notice, by the way, all these objects make perfect sense because continuous functions over compact intervals are integrable in the Riemann sense. So this integral makes sense. It's going to be a positive number, so or non-negative number, I should say, and that you can take a root. So that 1 over p root there is also well defined. Okay, so now we have to check that these satisfy the norm properties. There's 3 of them: positive definiteness, homogeneity, and triangle inequality. Now turns out the homogeneity and the positive definiteness, this is easy. So for instance, let's look at this guy here. So positive definite, well, so when is this integral going to be equal to 0? Well, since you're working with continuous functions, a result from real analysis says that's only going to happen when the function itself is equal to 0. The same here for this norm, by the way. I already call it a norm, although it's not established yet. So also here, this quantity is going to be 0 only because you're looking at the extreme value of a non-negative function. If that extreme value is equal to 0 and the function is continuous, that can only happen when the function is identically 0. Okay. The homogeneity is even easier because if you have here a lambda in here, you could just pull out the lambda out of the complex modulus and then out of the maximum. So you have it. And same thing on the integral level, right? Properties of the integral. You take a lambda here, it comes then out with a lambda to the power p, and then you pull it further out, and then the p goes out here with this 1 over p root. Okay, so this works. So now what needs more thought is the triangle inequality. Okay, so it is easy to check that the above are positive definite and homogeneous, but the triangle inequality requires more work when p is not equal to 1, 2, and infinity. And why is this? So when you're dealing with the case infinity, you have to look at the supremum. Well, how do you prove this? Well, you look at this. You use the ordinary triangle inequality for the complex modulus. You get this, and now you just optimize these things. So here, the first quantity is less than or equal than its maximum, taking over the interval from 0 to 1, and so is the second quantity. So you first have this, and since this inequality here, the chain of inequality, holds for any x between 0 and 1, well, then it also holds, of course, for the extreme value. So you immediately have this, right? Because this is f plus g infinity. So this works out easily for infinity. Okay. For 1, it is the same argument essentially. You just use properties of the integral. Okay, no further comment. Now for 2, this is maybe something you have seen in a linear algebra class when you discuss inner product spaces. We will do this later on in this class, because you can define an inner product on this space of continuous functions, and that inner product induces a norm. And since you have the Cauchy-Schwarz inequality for the inner product, you can get the triangle inequality for the norm as a corollary. But this only works for p is equal to 2. So for all the other p's, different from 1, 2, and infinity, 1 requires more work. This will require 2 inequalities. One is the Hölder inequality, and then the other one, a corollary to the Hölder inequality, is the Minkowski inequality. And once we have those, then we will realize that these norms on the space of continuous functions on intervals 0 to 1 are actually norms. Okay, but this I will do in the next video. Okay, see you then.